Okay, so we cannot continue a understanding of physics without hitting a little bit on the building blocks of matter. Building blocks of matter consist of these fundamental particles, if you want to call it that, of the atom. So the atom consists of electrons, neutrons, and protons, and something called quarks. And so as you get into the nuclear portion of understanding physics, these become fundamental units that are important to understand their properties, but also their sizes and how they relate to each other, because they become important when we start looking at the forces associated with them and the speed and the speed with which they move. A cube of gold, then, if we take a look at it, how many times can you cut the cube in half until it's indivisible? Theoretically, you can keep cutting it until you get it down to the fundamental unit. At some point, the gold cube becomes unsliceable, from which the word in Greek, atomos, comes. The English word for atom then was thus derived from that value. The atom was once believed to be the smallest and the ultimate particle of matter. But if we go back to this little jewel here, the quark, we find out in our studies that quarks are actually even smaller units associated with these fundamental units. So if we look at a gold cube, it's approximately 3.73 centimeters on a side for a 1 kilogram cube of gold. So is the cube of gold wall-to-wall gold? Are there any empty spaces? Well, the cube of gold at 1 kilogram, approximately 2 pounds, has a length of 3.73 centimeters or 1.5 inches on a side. If we look at its volume, cubing that value of 3.73 centimeters, we end up with a volume of gold of 51.9 cubic centimeters. It's important to start getting used to these units of measures, because as we move along, coming up with values of centimeters squared and centimeters cubed, as well as the single centimeter, become very important, and they can become very confusing as you start making your calculations and trying to determine, am I looking at a surface area, am I looking at a length, or am I looking at a volume associated with any particular problem? If we look at something called unit analysis or dimensional analysis, this can be broken down into its fundamental dimensions. As we said before, the fundamental dimensions being length, mass, and time. With any unit, there are at least these three fundamental dimensions associated with it. So LM and T become a dimensional analysis or a unit analysis associated with any fundamental or derived unit. For example, let's take a look at velocity. Velocity, which is defined as a length per unit time, typically in meters per second, we see that the length is divided by an amount of time and can be expressed as L over T. We can take the T out of the denominator and put it in the numerator, and it becomes L times T to the minus 1, or LT minus 1. So we have to be aware of these fundamental units, because they are very useful when we start to look at our analysis and back-checking to ensure that we do in fact have the correct units associated with our solution. If we look at an expression here, this expression particularly says that if we have a change in any distance, we can relate it to an initial velocity times time and add 1/2 of the acceleration times time squared. So if we dissect each of these terms in this relationship, we can see that delta x is really just a length, And velocity times time is just length times time times time. And then we add a unit of length times time squared times time squared. Notice that the constant 1/2 is removed when we do a dimensional analysis. So in checking this out, what we want to make sure is, does the right side equate to the left side or vice versa? So in this case, we want to know, does the length L equate to all of those L's and T's squared on the right side of the expression? So as we start going through this, we can start canceling out values. So if we cancel this T and this T, we're left with L. If we cancel this T square and this T square, we're left with L. L plus L ends up just being L. We know it's 2 times the length, but in this case, we get rid of the constant and we have L is equal to L. So this becomes a method of distinguishing physical quantities and is helpful in checking equations, since every equation must have the same dimension on both sides. In doing unit conversions, sometimes it's necessary to convert units from one system to another. A problem may be given to you in miles, but they want the answer in meters or kilometers. It may be given to you in feet, and they want the answer in centimeters. It may be given to you in meters, and they want the answer in feet. And so what you have to be able to do is understand that there are units of conversion or conversion factors that allow you to convert from one to the other. 1 mile is equal to 1,609 meters, or 1.609 kilometers. 1 foot is equal to 3.3048 meters, or 30.48 centimeters. And 1 meter is equal to 39.37 inches, or 3.281 feet. 1 inch is equal to 0.0254 meters, or 2.54 centimeters. So it's important to know that when you set up a relationship, that you might have to multiply or divide through by either of these conversion factors, any of these conversion factors, in order to derive or arrive at the units that the problem asks you to solve for. Units can be treated as algebraic quantities that can cancel each other out. So for example, suppose we wish to convert 15 inches to centimeters. So because 1 inch is equal to 2.54 centimeters, we find that 15 inches is equal to 15 inches times 2.54 centimeters per inch. So you can see that in the first term, the inches, and the second term, 1/inches, cancels each other out, and we're left with 38.1 centimeters. Whenever we set up a problem, we want to make sure that we have it set up that our conversion appears in the numerator. Notice that the inch units cancel out, leaving only the centimeter unit. So let's look at an example. The problem statement says, if a car is traveling at a speed of 28 meters per second, is it exceeding the speed limit of 55 miles per hour? So the first thing we need to do is perform a conversion in meters per second and convert it to miles per hour. So 28 meters per second, when I multiply through by 1 mile, is equal to 1,609 meters. Again, I set it up so that I have miles in the numerator and my conversions in the denominator. So in this case, the meters cancel out. I'm left with miles per second. So I get 1.74 times 10 to the minus 2 miles per second. But that's not what the problem asks for. The problem asks for the conversion to 55 miles per hour to determine if 28 meters per second is exceeded. Okay, so notice that the meters unit canceled out and it left with those miles per second. Now let's convert seconds to hours. So 1.74 times 10 to the minus 2 meters per second then is equal to that value times the first conversion factor, 60 seconds in a minute, times the second conversion factor, 60 minutes in an hour. And now when we multiply through 60 times 1.74 times 10 to the minus 2, we get 62.6 miles per hour. So we can see that 28 meters per second does in fact exceed the speed limit. Notice that the second and minute units canceled out, leaving only miles per hour. In looking at speedometer conversions, convert 20 kilometers per hour to miles per hour. Again, we do the same thing. We start with our term that we were given, 20 kilometers per hour, and we find the conversion. Well, since we're trying to convert from kilometers to miles per hour, we need to multiply through by the conversion factor. 1 mile is 1.609 kilometers. When we set this up properly, we have miles in the numerator, hours in the denominator, and we get 12.4 miles per hour as the conversion for 20 kilometers per hour. Notice that the kilometer units cancel out, leaving only miles per hour. What if we wanted to convert 25 miles per hour then to kilometers? Now you'll notice we invert our conversion factor, 1.609 kilometers, into the numerator per hour, per mile. So when we do this, we are left with kilometers in the numerator, hours in the denominator. 25 times 1.609 gives us 40.2 kilometers per hour. Notice that the miles units cancel out, leaving only kilometers per hour units. So we always want to make sure the units are correct in the numerator and the denominator when we set up our conversion factors. Significant figures is an area that plagues students throughout their studies in the area of physics, science, and engineering. So becoming familiar with the rules associated with significant figures becomes very, very important. So when we come back, we'll take a look at significant figures.